Here are solutions to homework set number 9 for ECE 320. This homework looks at MOSFETs being used as switches and CMOS logic. Now the first problem is given the VI characteristics for MOSFET, label the regions and calculate the transconductance gain K sub n. Well, the regions are off, ohmic, and saturated. Off is when the current equals 0. Saturated is over here in this flat region. And ohmic is on the left. And the transition between the two is when VDS is VGS minus V threshold. So here, the threshold voltage, let's get this out of the way, is the gate voltage goes 7, 6, 5, 4, 3, 2. It's less than 2. It's about all I can read from the graph. It's actually 1 volt. So 2 minus 1 is 1. So that's where I switch here. 3 minus 1 is 2. 3, 4, 5, 6. There's the transition. If VDS is less than that, less than VGS minus V threshold, I'm ohmic. More than that, I'm saturated. To calculate the transconductance gain is pick a point. In the ohmic region or saturated region, if I pick a point A, that's in the ohmic region. Here's the equation for the current in the ohmic region. I know the current from the graph. I know VGS, I know V threshold is 1 volt. I know VDS, calculate K sub n, I get 1.67 milliamps per volt squared. If I pick point B, that's the saturated region, I then use the saturated equation. I know I sub ds, I know VGS, V threshold, calculate, I should get the same answer. They're different just because I can't read the graph to 7 decimal places, but they should be pretty close. Problem 2 says draw the load line and then label the operating point. The load line is when the current is 0, I have 10 volts. When the voltage is 0, I have 10 over 400, 25 milliamps. There's your load line. If VGS is 0 volts, I'm at this point A, I'm turned off. When it's 4 volts, I'm right here, and I get VGS. VDS is 4 volts. IDS is 7.5 milliamps-ish. And when VGS is 7 volts, I enter the ohmic region. It's now right around 2.3 volts and 18 milliamps. Again, we do a lot of load lines in this class. I've got to be on the load line somewhere, and the gate voltage tells you where you are. Now, kind of a sidelight, MOSFETs have two functions. Over here, it's a voltage-controlled current source. I can set the current by the voltage, and it's a square law. That's why it's uneven spacing. Over here, a MOSFET is a voltage-controlled resistor. If you look at the slope right here, the slope is 1 over R. As I change the voltage, I change the resistance. Problem 3 looks at using a MOSFET as a switch. Now, if you go to DigiKey and you find the stats or the data sheets for an IRF 3710 MOSFET, one of the MOSFETs used in Circuit Lab, here's the specs. From this, I can get the transconductance gain. The one you care about is this one right here. This is the resistance telling you ohmic region under certain conditions. Here's the equation for the ohmic region. I know IDS is 28 amps. I know VGS is 10 volts. V threshold is somewhere between 2 and 4 volts. Let's assume 3. VDS I can get. Voltage is I times R. I've got 28 amps at 0.023 ohms. Gives you 0.644 volts. Plug it in. I solve for Kn. And it's going to depend upon what you use for the threshold. At 2 volts is 5.66 amps per volt squared, 6.5, 7.6, something in this range. Now with BJT transistors, the current gain beta varies quite a bit. For example, with a 3904 transistor, the gain is somewhere between 100 and 300. On MOSFETs, the threshold voltage varies quite a bit. Problem 4 says, okay, let's calculate. What's the operating point, meaning what is IDS and VDS for this circuit when Vn is 0 volts, 5 volts, and 10 volts? And we're going to use the parameters used in Circuit Lab, where K sub n is 48, V threshold is 3.39. Well, when Vn is 0, I'm less than V threshold, so the MOSFET is off. When you're off, you're at 10 volts, 0 milliamps. Again, kind of think of the load line. I've got this characteristic. Here's your BDS, V, or IDS. If I'm less than V threshold, I'm operating right here. I'm off. When Vn is 5 volts, or Vg is 5 volts, I don't really know, am I ohmic or saturated? Let's guess saturated. If I do that, I know VGS, I know V threshold, I know K sub n, calculate IDS, 61 amps. Find VDS, I'm at minus 484 volts, which is way over here. That's not possible. I can't have a negative voltage on this circuit. What that tells me is my assumption was wrong. I am not saturated, I'm actually ohmic. So, try the ohmic model. Here's the ohmic model. I've got two unknowns, IDS and VDS. Here's the MOSFET model. I've got a second equation. I need two equations for two unknowns. The second equation is the load line. 10 volts is 8 times IDS plus VDS. Two equations, two unknowns, solve. Here I would use numerical solutions. I guess VDS, solve for IDS, guess VDS, plug it in the first equation, solve for IDS, see if the second equation balances. If it doesn't, that's my error. Keep iterating until the second equation balances. That's my solution. And when I do that, there's actually two answers. This is a parabola that looks kind of like this. And at my load line, there's going to be two answers, one on the left, one on the right. I want the one on the left. So when I do a numerical search, I'm going to start with VDS close to 0, or IDS is close to 10 over 8, 1.25 amps. Keep iterating until the answers balance. And there's your solution. There's also a solution over here. If you get a nonsense answer, you got the wrong solution. So that's the correct answer when VGS is 5 volts. And as a check, VDS is indeed less than VGS minus V threshold. This is ohmic. Repeat, change this to 10 volts, and again do a numerical solution, and I get that answer. Basically, VDS is almost 0. That's kind of where MOSFETs are really good switches. For an ideal switch, I want VDS to be 0. It's not 0, it's not a perfect switch, but 0.01 volts is pretty darn close, or 0.003 volts is pretty darn close. This makes just a great switch. That's one of the reasons MOSFETs are used in industry rather than BJTs. We don't use them in lab because they're sensitive to static and they don't survive our lab conditions. If you have a more controlled lab condition, MOSFETs are much superior. Then simulate. If I throw the circuit into Circuit Lab and simulate, here's what I get when VGS is 0 volts. Sure enough, the current is 0, both calculated and simulated. At 5 volts, I calculated 16 millivolts, simulate 37 millivolts, basically 0. At 10 volts, I calculate 3.9 millivolts, simulate 24.9 millivolts, basically 0. If you look at Circuit Lab, they actually have a small resistance in series. There is a small resistance in here. I times R starts to matter when talking about 0.003 volts. From our standpoint, it's basically 0, close to 0. The last problem is CMOS logic. Now, this is kind of a neat thing about CMOS. I don't have to go through the and OR gates. I can do it all at once. To come up with the logic to implement this function, I can circle the ones or circle the zeros, your pick. I personally prefer zeros. If you circle the zeros, I get Y bar, because I circled the zeros. That's A bar D, or A C D bar, or A B bar D bar. If I use De Morgan's law, I get Y is this combination. This is basically how I implement it. If I have, put this down here, A bar D or A B D bar, I'm going to spell D. Try that again. Or A, C, D bar. That's the logic down here. That's a B. That's Y bar. The reason I like doing Y bar circled with zeros is because that gives you the logic down here. When these are true, Y is pulled low through like 0.01 ohm. So that's the Y bar. It's pulled low. In MOSFET logic, series is AND, parallel is OR. So that's A bar B, D, A bar D, or the second term, A, B bar, D bar, or A, C, D bar. That's the low side. High side is De Morgan's law. Series becomes parallel, parallel becomes series. So this one is A bar D in parallel. The second one is A, B bar, D bar in parallel. Third one is A, C, D bar in parallel. All these are put in series. That's De Morgan's law. Put it all together, here you have Y in one shot, which I think is kind of neat. Anyway, that's homework set number 9 for ECE 320.